So I will talk about effect of pre-planning process on low cycle fatigue behavior of high strength steel and using infrared thermography to detect the behavior of material subjected to low cycle fatigue. So there are a lot of applications that they are subjected to heavy loads, like these cranes that you see. They are lifting a lot of weights, and there are a lot of points actually. They are already plastically deformed. So the low cycle fatigue is really important actually parameter for these applications. And also we know that there are a lot of parts in these applications that they are bent as well. So in this talk I will talk about the problem, what is the problem when we bend and we apply low cycle fatigue conditions, and then I will talk about the new experimental setup that we developed to solve this problem, and then the numerical modeling approach that we use to estimate some stress levels and to predict the lifetime, and at the end hopefully I can give you some suggestions on what can be done when we combine bending and low cycle fatigue. So let's talk about introduction. As I said, we have a lot of parts here that they are lifting heavy weights, and at the same time they are subjected to bending. So we have a complex multiaxial stress distribution inside the bending area. These kind of steel grades, they are really good for mobility actually, and what they are monitoring is not having any crack outside of the bent area. But when they are subjected to fatigue loads, we are afraid that there will be some cracking inside let's say, the bent area. So the main objective is to solve this problem and to combine these two phenomena together. So the experimental setup that we developed, actually, first we thought, okay, there are some fatigue samples, it's a dog-bone specimen, and then we wanted to see the effect of bending. So we took some ASTM standard dog-bone samples. We increased actually the width of the specimen because we wanted to have a kind of plane strain condition in the middle of the specimen, and then we bent the sample. And you see here it's a bent sample. So we wanted to test under fatigue loading conditions, so we had to weld two samples together to have a symmetric condition. And you see here we did some data acquisition using strain gauges, and also we used thermography, which I will explain later. So that was the initial idea, that we just wanted to combine the low cycle fatigue and bending concept. So from the acid curve, we can see we tested this at 0.2 stress ratio 0.1 at 2 Hertz, and we see a quite good actually response of the material. And when we wanted to detect the onset of crack initiation, which is interesting for us, we tried to monitor the displacement. Let's say it's fixed here, the load is applied here, so we monitor the displacement at crosshead. And we found out the trend is a little bit complex. We cannot find any indication in these areas, so we said, okay, let's see what will happen if we have, let's say, 0.1 millimeter after stabilization. What is happening? Is there any cracking there? So we separated these lifetimes at that point, so for all these tests, and we could see that almost 80% of the total lifetime is spending till this point. But for sure we don't know what's the crack size there. Then we did some actually extra, let's say, investigation. So also we wanted to investigate the effect of surface, because most of the case when they apply a surface treatment to bend this material, and we wanted to see what would be the effect of surface treatment, bending, and low cycle fatigue. So what you see here, basically it's a virgin specimen, and we have grinding. We removed 0.1 millimeter from the specimen before bending, and then we applied bending, and then we applied shock pinning before and after bending. We see that at the higher stress levels, there is not that much influence of surface treatment, and that's clear because from the first cycle, you're releasing the residual stress which you are applying using grinding or shot pinning or whatever technique that you use. But at some level, we see some improvement. For instance, at this stress level, we see that grinding gives us a little bit better, and at these two stress levels, we see that grinding and shot pinning, they are improving the total lifetime. So the main reason is, of course, the residual stress, which is associated with the process that we use. For instance, for grinding, we know that we use conventional grinding approach, and from literature, we know that this kind of grinding can induce really positive stress at one side, and when it goes down to the specimen, we will induce some negative stresses, which of course is interesting for us. But this is the stress distribution before bending. When we apply bending, this part is shifting to negative side. So we have a negative stress on the surface because of bending, and we have negative stress because of grinding. So these two would be added together. But for shot pinning, actually, from the beginning, we have a negative value of stress before and after bending. But when we apply bending, when we apply shot pinning and then we bend the sample, there is no added value because we are already decreasing or damaging this residual stress which we induced on the flat specimen. So then we just wanted to compare using the same assumption, let's say 0.1 millimeter displacement. We don't know yet. I will explain what is the crack length in that displacement later. So we wanted to just see what is the effect of different, let's say, process surface treatment on the total lifetime and on initiation and propagation. So we see that the initiation lifetime is, as we expected, the initiation lifetime is really improving by applying the, let's say, the bending, the shot pinning and grinding at low stress levels, but at high stress levels, as we expected, there is not that much improvement, but we see some improvement in crack propagation, which is the reason for that is we have high compressive stress beneath the surface. When the crack is propagating, the compressive stress just some sort of closes the crack and does not it does not let the crack propagate faster. So then, as I said, we wanted to see what is the crack length at that let's say 0.1 millimeter displacement. So we cut our samples like this in the middle of samples, and we have two sides, of course, we embedded in epoxy, and at 0.1 millimeter at 40, I think at this level, we tested all our samples at this stress level. We could see around 0.65 millimeter crack length, which of course it's a long crack. It's not a short crack, and it's a long crack. So we know that it takes let's say 0.1 millimeter displacement to form a long crack. Then we tried to cross-section the rest of samples. Let's say also I wanted to see the effect of surface treatment, and we got some strange results. One of them is strange, which is that grinding after bending, which we had a better lifetime, but of course the crack length was 1.7 millimeter, but the rest, the crack lengths for shot pinning after and before bending, they are less than the virgin specimen. I believe the main reason for this changes, this high value of crack length, is that it took longer time for that grinding to initiate the crack, so that the long crack formed really long time after the initiation. So if we compare these all together, I think it's reasonable, because we had much more higher lifetime for initiation for grinding condition. So again, we didn't want to stop here, because we didn't know that what is the basic behind that, why it's forming like that, and I was pretty sure that the crack is being initiated much more sooner than we have right now. So we did also some fractography, and we wanted to see for this high strength steel, which they are subjected to really high stress at bending group, so there are a lot of plasticity there. But the fracture surface that we see is quite brittle. As you can see here, multiple cracks initiated inside the bending area, propagating up to 3.5 millimeters. And if we look at to this area, we cross section it, we can see that okay, the crack, this is the fatigue crack, 3.5, and the rest is the tensile fracture. We also stopped the test at 10,000 cycles at the same load, and we found 0.4 millimeter crack length. So even at 10,000 cycles, we could see some small cracks, but it's relatively big crack, of course, 400 micrometer. And then we tried to use thermography to detect the onset of crack initiation. So we just monitored, actually, when the test was running, we monitored inside the bending area, and we used some correlation, which is called lock-in thermography, because the temperature that we measure here includes all the environment temperature, first and second harmonic temperatures, and inelastic and elastic. So we wanted to filter it out. So then we used some sort of correlations to improve the signal-to-noise ratio. And the first test that we did, we stopped the test here because we didn't want to use the camera actually during the test, and we started again here. As we can see here, the red curve is the temperature. Actually, it's 100 cycle, 5,000 cycles, and this is 12,000 cycles, and we extracted this at this point, R5. It's at the middle of our specimen. So, and then we can see clearly the crack is being formed, and again, at this number of cycles, 5, we see that the big crack is there, and then finally a fracture. So we know that this is 0.1, which we had in mind that it can be a long crack initiation site. So we know that at this point the big crack is forming, and the reason for this drop is we believe that when the crack goes into the material, the heat transfer to the surface is decreasing. So because the hot spot is at the crack tip, so the camera cannot see the heat source, and that's the reason that let's say the temperature is dropping, and at final rupture, the crack is really open, so the camera sees the crack tip. So that's the main reason for this behavior. But as you can see here, it's an experimental temperature. So we wanted to filter it out. So we filtered out the temperatures using just the correlation that I showed, and we can see that we have phase 1, phase 2 for crack initiation, and phase 3. We did it also for, which is a crack propagation, we did it under displacement control. You see the comparison between displacement and force control here. It's almost the same behavior. We have a crack initiation and crack propagation phase. This one includes short and long crack propagation. So I also tried to model the same behavior because we wanted to see what is the nature of stress at the bending root. So we bent the sample, and after bending we applied some spectral patterns, and we just measured after the bending. And you see this the comparison between simulation and the experimental results are quite good. And then we used the double symmetric boundary condition, and we applied fatigue load to the specimen. And using the strain gauges that I showed, we could actually validate the model inside and outside of the specimen. And then we monitored the stress distribution inside the specimen, but we had multiaxial stress in 3 different directions. But from these results, because of time, I won't go into details, but we could detect that the stress along the L2, which is the thickness, is really sensitive to the distance from the notch root. So the stress gradient should be taken into account. Then we use some sort of damage modeling approach using a damage model from Lemaitre. So then we know that the voids are initiating during low cycle fatigue. So we take into account triaxiality, which is the reason for expanding the load. And then we, as I said, we took into account the gradient effect for finding the critical distance. As the triaxiality is really important, I tried to monitor the peak value of triaxiality and to find the critical distance, and then the stresses were, the stress gradients were calculated in this distance, which is around 0.5 times of the thickness. And then finally we applied, we calibrated the data to get the material constants, and we applied to different stress ratio, and these are the simulated results that you see here, and the correlation is good. To conclude, I have to say, okay, we wanted to solve the problem of bending and fatiguing at the same time. We came up with the test design, test setup, and then we tried to investigate the effect of surface treatment, which is important, but it depends on the stress level. And also, we think that thermography is a good approach to use to solve this problem. And numerical modeling, of course, gives us a better understanding of the problem. Okay, that's all. Thank you.